that there. Go ahead and share the screen. Oop. Molly on here. There we go. So good. So let's continue our conversation of what happens when waves encounter boundaries. So this is what we started last time. So again, what we have is a wave that then is going to encounter the boundary. And then we're going to get different things going on depending on what we're looking at here. So basically, we've been concentrating on the reflected part. So typically when a wave encounters a boundary, we have two pieces. We have a reflected wave, reflected, and then we also have a transmitted wave. So transmitted. So the reflected wave is the part we've mostly been looking at. That's when the wave encounters the boundary and then bounces off the boundary and then comes backwards. And the transmitted part is the part which goes into another piece of medium. So the reflected portion stays inside the same medium, stays in the same medium. And then the transmitted part basically passes through the boundary and then goes into a new piece of medium. So goes into a new medium. Okay. So what we saw last time was, at least with the reflected part, so let's concentrate on the reflected part for a second. We saw that we can have one of two scenarios based off of the type of boundary. So we had the unfixed boundary, and we had the fixed boundary. So for the unfixed boundary, what we saw was that the wave stays in phase. In phase with the original wave. And then for the fixed boundary, we saw that the wave is out of phase by pi radians. Right? So just kind of quickly remind you, so let's bring up our beautiful simulation again. So move everybody here. So good. So again, here what we have is what? So let's send in a pulse. So we're going to create in a pulse. So again, with our fixed boundary, so this is what we have initially. So the fixed boundary, again, we're going to send in our wave pulse. That's then going to encounter the boundary. When it encounters the boundary, then it gets reflected out of phase by 180 degrees. So again, this is another fix. So again, it gets reflected by 180 degrees. And then if we had a loose or unfixed boundary, so again, here we see this guy come in. And then at the boundary, it doubles in size of the amplitude, and then the reflected wave portion is exactly in phase with the original. So, and again, for the unfixed, so at the boundary, the amplitude goes to twice of the amplitude, so it ends up being doubled. And then here for the fixed boundary, so at the boundary, the amplitude goes to 0. So at any fixed boundary point, it has to be what we call a node. So here, this is what we call a node. So it has to be fixed at 0. So again, the way that we described this was we said we had two waves coming in. One was a real wave moving, in this case, from the left. And then we had an imaginary wave, which is moving from the right. And then those two superimposed on top of each other via our superposition principle. So this is discussed via superposition principle. So let's again kind of redraw all this. So for our unfixed, so again, here we have the initial wave moving here to the right with a velocity v with an amplitude of a. Here's our boundary. At the same time, we have an imaginary wave which is moving in. I'll draw that with the green. With exactly the same amplitude in phase, just in this case, moving to the left. So that way, by the time they get to the boundary, so here is my left moving wave. We'll go by using blue. And then here is my, there we go. There is my right moving wave, so that the two of those superimpose on top of each other to create a wave which has exactly twice the amount of amplitude. So this is twice our amplitude. For the fixed endpoints, so again, we have this guy coming in from the right, moving here. But now, as we encounter our boundary, the green one, which is going to move in from the right, is completely out of phase. But again, moving with exactly the same velocity, with exactly the same amplitude. It's just that they're out of phase by 180 degrees. Or pi radians. So this is our amplitude A. So by the time they get to the boundary, again, this one is upward. This one is downward. So that the net result of these two is exactly 0. So using terminology we talked about on Friday, this is what's known as constructive interference. And this is what's known as destructive interference. And again, in a general sense, constructive interference just says that the two amplitudes of the two waves sum together. So this becomes the total amplitude. So just in case they don't have exactly the same amplitude, then in this case, they would just sum together with the total amplitude. And then here we would get a, say, A1 minus A2 is then equal to the total amplitude. So here the total amplitude would then just be the difference between the two amplitudes. So if they don't have exactly the same amplitude coming in. So this is all with the reflected portion, but what happens with the refracted portion, or what we call the transmitted portion? So let's quickly talk about the transmitted portion. So transmitted and also what's known as refracted. So with the transmitted wave or the refracted wave, what actually ends up happening is that the frequency of the wave after it has passed from one boundary to another boundary stays exactly the same. So as a wave goes from, say, medium 1 across the boundary to medium 2, what happens is that the frequency of the wave stays the same. So the frequency remains the same. Oops. I know how to spell. There we go. Remains the same. So basically what that means is, for example, when you play a guitar and you strum your strings, what's happening is the string is vibrating at a particular frequency, and then when it passes from the string into the secondary medium, i.e. the transmitted wave goes to the air, you hear the same exact vibration of the string. So when you play a G string, it's vibrating at a particular frequency, so then you hear that same exact frequency as it passes from the string into the air. So you get to hear it exactly the same way. Or when I bang on my desk, what that is doing is it's vibrating at a particular frequency. The frequency of vibration then is exactly the same that you would hear in the air as what is happening inside of the desk itself. Maybe it'll show up. Oh, they did. Okay. So, but what's going to be in general true is that the velocity of the speed in one medium is going to be different than the velocity in another medium. So if this is, say, my boundary point, and then this is, say, medium 1, and then over here we have then medium 2, what's going to be different is, since they're two different mediums, what that means is that the velocity of the speed of the wave in medium 1 will in general be different than the velocity of the speed in medium 2, but the frequency in medium 1 must be the same as the frequency in medium 2. And since we know that the velocity is equal to the frequency times the wavelength, what that also means is that the wavelength has to change. So as the wave is moving from one medium to another medium, in general, then the wavelength is going to change because the velocity changes, but the frequency has to stay the same. So what this means then is the ratio, using this expression over here, that the velocity to the wavelength must be the same in both mediums. So if I took the ratio of these, because this is simply equal to the frequency, since the frequency is the same in each medium, that means that the ratio of the velocity to the wavelength must remain fixed as it passes from one medium to another medium. But again, since the two frequencies are the same, but the two velocities are different, that means the two wavelengths are also going to be different. So as the wave passes from one medium to another medium, the wavelengths will be different, but the frequencies have to stay the same. So good. So we're using all this to then talk about what's called standing waves. So let's talk about standing waves. So again, what is a standing wave? So the standing wave is, we're going to send in this right moving wave. That's then going to encounter a left moving wave, and then the superposition of those two waves on top of each other creates the standing wave. So again, here I have a moving wave, which is moving from right or from left to right. In the imaginary section, I have exactly the same wave, but out of phase by 180 degrees, moving in the opposite direction. So we have two traveling waves, one moving this way, one moving this way. These two then are going to superimpose on top of each other to then create this standing wave. So again, let's send in our oscillation. Good. So this guy's moving to the right. We have an imaginary one moving to the left. They then incorporate at the boundary. That then creates the fact that this guy now is only oscillating up and down. It's not a traveling wave anymore, which then creates this standing wave. So again, let's watch that one more time. So again, a standing wave is when this thing is only oscillating up and down. I have this point here, this point here, this point here, which are all what we call nodes. Okay. And again, this is also true if I did no endpoint. Let's restart this and send this guy going in this direction. Oh, sorry, not no endpoint. I want an unfixed endpoint or loose endpoint. There we go. So again, even with an unfixed endpoint, this guy would move in, encounter at the boundary. Now the difference is instead of having a node at the boundary, it now has to have twice exactly the amplitude. But again, we're going to create these standing waves. So what we're going to concentrate on now is when I have two fixed endpoints. So let's look at a standing wave. So standing wave with two fixed endpoints. So for example, this is going to be a standing wave on a string. Let's say on a string. So this is like your guitar string, violin string, harpsichord, all kinds of different stuff. So let's say here's my string. So this is one fixed endpoint. So this guy's fixed. Here's my other fixed endpoint. And then this length of string is going to be some length L to it. Okay, so this is going to be my string L. So we can then create different wavelengths on the inside of the string. So for example, we could have simply that this guy does this. Right? So this guy's going to move in, and then this guy does that. So this guy's going to oscillate back and forth to create this one kind of lobe here. So this guy's going to oscillate back and forth. Okay? So this is one example we can have. Or we could have an example where, again, here's my fixed endpoint. This is my fixed endpoint. This guy could instead be oscillating like this. So this guy comes up, down, back around. So this guy's going to oscillate around here, where this guy now has more nodes. So here, this one has 2 nodes. Usually we don't count this one. So this one only has 1 node. This guy has a node here, a node here, and a node here. But again, we usually don't count the first one. So this actually has 2 nodes. Another example could be that I have this guy here. Here's my other fixed endpoint. This guy is going to be oscillating like this. There we go. So this guy can oscillate like that. So this guy actually has then 3 nodes. So I have a node here, I have a node here. You can draw that right. So this one actually has 3 nodes. Right. So again, nodes are where this guy doesn't oscillate up and down, and etc. Right. So one thing we can look at then is we can count how many wavelengths are inside of the length of the string. Right. So remember, this entire thing is actually a wavelength, because it has to go all the way up to maximum, down through 0, down through minimum, back to maximum. So this is actually half a wavelength. So here we can say then that 1/2 of a wavelength is inside the length of the string. For this one, it's an entire wavelength then is equal to the length of the string. For this one, then we have 1.5 wavelengths, or 3/2 of a wavelength then is equal to the length of the string. And if I drew another one, so let me draw one more on here. Let's put that one over here. So in this case, another one I could have would be this guy. This guy would do that, and that, and that, and that, and that. And then create this scenario. I think I drew too many, so that's 1, 2.5 wavelengths. So in this one, I would have what, 5/2 of a wavelength. You can also have one with just 2 wavelengths. Let's draw one more. So I'll have 2 waves. Let's see here. There. Good. So that guy. Good. And then this guy would be what? 2 total waves. So here I would have 2 wavelengths that is equal to the length of the string. So basically, what this kind of tells me, what these pictures are kind of showing me, is that anytime I have fixed endpoints like this, 2 fixed endpoints, for example, you can then only have certain numbers of wavelengths which go inside of this section. So what the first one shows is I can have exactly half a wavelength. In the second one, I have a full wavelength. And the third one, I have 3/2 of a wavelength. Next one then is 2 full wavelengths, and then 2.5 wavelengths, and then 3 wavelengths, and etc. So basically what this says is that anytime I have a standing wave with 2 fixed endpoints, what has to be true then is I can fit only certain wavelengths inside of this region. From each one of these, this one tells me then that what? The wavelength then is equal to twice the length of the string. This one tells me that the wavelength is equal to the length of the string. This one tells me then that the wavelength then is equal to twice the length of the string divided by 3. This one then tells me that what? The wavelength then is equal to the length divided by 2. This one then tells me that the wavelength then is equal to twice the length divided by 5. But here I have 1 node, here I have 2 nodes, here I have 3 nodes, here we have 4 nodes, here we have 5 nodes. So we can see then is actually this is building a pattern. So the wavelengths that can actually fit inside of each one of these sections then is equal to twice the length of the string divided by the number of nodes that we have. Okay? Because here, this is the same thing as divided by 1, which I have 1 node. This is twice the length of the string divided by 2, which is the double number of nodes. This is twice the length of the string divided by 3, which is the number of nodes. This is the same thing then as twice the length divided by 4, which is the number of nodes. This is twice the length divided by 5, which is the number of nodes. So for a string, or at least for a standing wave with 2 fixed endpoints, the amount of wavelength which I can fit inside of the region then is equal to twice the length of the string divided by n, where n is the number of nodes. So n is equal to the number of nodes, which is also what's known as the harmonic. So again, all this says is that anytime I have a standing wave with 2 fixed endpoints, what has to be true is we can only have certain frequencies which are allowed to exist along the length of the string. These different frequencies which are allowed to exist are then all of these different examples plus an infinite number of all their possible examples as well. So that means if you were playing guitar, you strum the string of your guitar string, it's going to vibrate at exactly one of these particular frequencies. So each one of these wavelengths also corresponds to a given frequency. We know is that the frequency then is equal to the velocity divided by the wavelength. That just comes from the velocity is equal to the wavelength times the frequency, which is then going to be equal to the velocity times the harmonic divided by twice the length of the string. So this is the allowed frequencies which are allowed for the string is allowed to vibrate. So these are the allowed frequencies of vibration. So again, anytime I have a wave on a string with two fixed endpoints, I can only fit certain frequencies inside of the length of the string. Each one of those wavelengths then corresponds to a particular frequency, so these are the only frequencies which we're allowed to hear as this thing is actually vibrating. Now, some terminology, when I have n is equal to 1, this is what's known as the fundamental. So n equals 1 is our fundamental, in this case, fundamental wavelength, and in this case, this is going to be our fundamental frequency. So when I have f1, this is what we call the fundamental frequency. This is the lowest possible vibration that a string can actually have. Okay. Anything above that, so for f2 and greater, these are what are known as the harmonics. So n is equal to 2, for example, is the second harmonic. N equals 3 is the third harmonic, and etc. Okay. So again, anytime that we have a standing wave on a string, for example, which has two fixed endpoints, this thing can only vibrate at particular frequencies, where the fundamental is simply this one. So this is our fundamental, where this guy is just simply oscillating back and forth like this. So this is our fundamental. And again, for this fundamental, this thing will be vibrating. As this thing vibrates, it has a particular frequency based off of this particular wavelength. So these are the allowed fixed frequencies and allowed fixed wavelengths for a string vibrating, or yeah, a string vibrating. So let's do an example. So this says that we have, is this one I want to do? No, that's not it. There it is. So we have a harpsichord string of length 1.5 meters and a linear mass density of 25 milligrams per meter vibrates at the fundamental frequency of 450 hertz. Okay? So first thing we want to know is what is the speed of the transverse wave on the string, and then what is the tension, and then we want to know what are the wavelength and frequency of the sound in air produced by the vibrating string. And then here we're going to take that the speed of sound in air is 340 meters per second. Okay? So again, what do we know? So we know that we have a length of string of a harpsichord. Does anybody know what a harpsichord is, by the way? A harpsichord is actually similar to a piano, but with a piano, what you have are little drums that basically beat on the string. So when you push down on the keys, it has a little hammer that basically hits the string, and then the string actually vibrates. A harpsichord is actually a little hook. So what happens is when you push the key, it actually plucks the string. So it's actually kind of a cross between a piano and a harp, basically. So instead of hammering on the string, you actually pluck the string. So that's actually a harpsichord, but it's kind of the same idea. Anyways, so let's see. So we have a length of string. So here's my string. We know this thing has a length equal to 1.5 meters. We know this thing is going to vibrate with a fundamental frequency, F1, which is equal to 450 hertz. Okay, so that is our fundamental frequency. We know has a linear mass density of 25 milligrams per meter. So let's write that down. So we know it has a linear mass density of 25 milligrams per meter. Okay. Any other information we need? That's about it. Okay. So last thing is we know the speed of sound in air for the last part is going to be 340 meters per second. Great. So let's look at part A. So for part A, first thing we want to know is what is the speed of the wave on the string? So this is what we want to know. Okay. So how would we do this? Well, we now know that the fundamental frequency is equal to the harmonic times the velocity of the speed on the string divided by twice the length of the string. So this is
What does mu mean in this case?
Mu is what we call the linear mass density. So it's the mass per unit length of the string. Okay, so this has to do with the property of the string itself. So this is the, so that's what we call the linear mass density. Of the string. That's right. So this is the mass per length. So this is mu. That's right. So good. So here, we know that this is the fundamental. So in our case, the fundamental, again, corresponds to n is equal to 1. So this means that the fundamental frequency corresponds to the velocity divided by twice the length of the string. So here, we know the fundamental, that's told to us, that's 450. We know the length of the string, we're told to us that's 1.5 meters. So from here, we can then solve this to get the velocity of the speed, the wave on the string. So this is then going to be equal to twice the length of the string times then the fundamental frequency. So it's going to be 2 times 1.5 meters times 400. Oops. Okay. So times 450 hertz. So good. So times 450 hertz. So that's going to be equal to, so that's what, 4,000, 12,000. Oh, wait. Good. So this should be 1350. So that is 1,350 meters per second is then equal to the velocity.
How do we know that n equals 1?
Oh, because it's a fundamental. So anytime that we have the fundamental, so the fundamental by its definition is for n is equal to 1.
Did the question say that?
Yes. So let's go back to the question. So it says here has a fundamental frequency of 450 hertz. That's right. So it was told in there. That's right. So otherwise we would have to know exactly what the harmonic is. So if we're told that it is fundamental like it does in this one, we automatically know it's n is equal to 1. Otherwise, it would either have to say it's the second harmonic or, you know, n is equal to 2 or give us that information. That's right. Good. So part B then wants to know, what is the tension in the string? So we want to know that the string here is being pulled, meaning that there's a tension force in this direction, and say a tension force in this direction. And what it wants to know is, what is then the tension in the string? Well, we know that, going back to what we did on Friday, I believe, that the velocity in on a string is also given as the square root of the tension divided by the linear mass density. So anytime that we're dealing specifically with a string, then the velocity in the string is given also by the square root of the tension divided by the linear mass density. Now here, we're looking for the tension, so that's this part we're looking for. We know the linear mass density, so we know that. And now what we know is that the velocity in the string here has to be the same as this velocity of the string here, so we also know the velocity in the string. So meaning that this velocity has to be the 1,350 meters per second. So from here, we can then solve for the tension. So this says that the tension then is going to be equal to the linear mass density times the velocity squared. So it's going to be equal to 25 milligrams per meter times then 1,350 squared. Now here we just have to make sure we put the milligrams into grams. So this says then that the tension in a string then is equal to 45.6 newtons. So this is then the tension in the string. Okay. Is it okay? So far, so good. Now, part C then wants to know, what are the wavelength and what are the frequency of the sound in air produced by the vibration of the string? So let's go to the page. So part C. So part C is now saying that what? So now we have the fundamental. So here is the fundamental. Here's the length of the string. So this thing we know is vibrating with a frequency equal to the fundamental, which is 450 hertz. So now what it's asking is, now the air here is also going to be vibrating. So here's the air, and it's asking what is the frequency in air that we hear, and also what is the wavelength that this thing has. So if this is my wavelength, what is the wavelength in air? So this is also what we want to know. So again, what's happening is this thing is vibrating at the fundamental, which means that once it hits the boundary, part of it is refracted or transmitted into the air, and we're hearing that transmission. Now, as we just talked about, what has to be true is that the frequency in air has to be exactly the same as the frequency of the original wave, which in this case is simply the fundamental. So the frequency it vibrates in air is the same as the fundamental frequency, which is then just simply 450 hertz. These two things have to be the same. Okay? But what we know is that the velocity on the string is 1,350 meters per second, but the velocity that we hear in air is then equal to what, 340 meters per second. So this means that since the frequency is the same, the wavelength cannot be the same. So since we know the velocity in air, we know the frequency, we can then solve for the wavelength in air. So we know the velocity in air then is going to be equal to the wavelength in air times then the frequency in air, which is the same thing as the fundamental frequency. So the wavelength in the air then is going to be equal to the velocity in the air divided then by the frequency in the air. So this is going to be the same thing as 340 meters per second divided by 450 hertz is equal to the wavelength in air, which is then equal to, what's that, about 3/4? About 0.76, good. So about 0.76 meters. So this is the wavelength in the air. Everyone okay? Not too bad, right? Okay. Hopefully. All right. So that brings us to, we're going to do 2 group assignments then. If we'll be good. So we'll spend the rest of the time, have you guys talk to each other, do all that good stuff again. So first one then says that we have a longitudinal traveling wave is moving in air with a speed of 340 meters per second. So one thing we talked about when we talked about the mathematical description of a wave, so let me bring that back up, where we said that the wave was described as the displacement at a position at a time was equal to A times cosine of omega t minus plus k times x plus phi. This is actually true for any type of wave. Doesn't matter if it's a longitudinal wave or a transverse wave. This is true for both. So this is true for both a transverse and longitudinal wave. So mathematically, these two things are described by exactly the same thing, as long as they are traveling waves. So this one says we have a longitudinal wave, but again, it doesn't matter. All that matters is that it's a wave. So here we're told that the speed of the wave is 340 meters per second, and we're told that time is equal to 0, and air molecule at x is equal to 0 has a displacement of 1 meter from its equilibrium position and is currently not moving. So basically meaning it's at maximum displacement. The maximum speed of the air molecule is 100 meters per second. So from this, what I want to know is, what is the frequency of the wave? What is the wavelength of the wave? What are the amplitude, the wave number, the angular frequency, and the phase constants? Meaning, what is this phi here? And then finally wants you to write down that d is equal to a, well, here it is sign, traveling wave, in the waveform of this using the correct sign. So again, we said that the plus sign means it's moving one way and the minus sign means it's moving the other way. So this is the first group assignment. The second one has to do with standing waves, what we just kind of went through. So it says that the portion of a cello string between the bridge and the upper end of the fingerboard, the part of the string that is free to vibrate, is 60 centimeters long. So it just means the neck of the string is, or the neck of the cello, the length of the string is 60 centimeters long. And this length of string has a mass of 2 grams. Okay? So it says the string sounds when it's at the total length of 60 centimeters as a fundamental frequency of an A4 note, which has a vibration of 440 hertz. So this is the fundamental frequency. So then it wants to know, where must the cellist put their finger, at what distance from the bridge all the way up to the position we're going to play the note, to play a D5 note, which has a frequency of 587 hertz. So here we are told that the A4 and the D5 are both fundamentals. So let's kind of draw what's happening here. So here is the neck of the cello. So here's the neck, where down here is the bridge. So this is the bridge. And we're told that this thing has a length of L equals to 60 centimeters. And then we're said that when this thing is played, this is going to have an A4 note, which is equal to the fundamental frequency, which is 440 hertz. This is 440 hertz. So then we want to know, where does the cellist have to put their finger? So let's say their finger has to go here. So we want to know this distance here. Let's call that guy X. So what is X equal to? For this thing to be able to play the D5 note, which then has 587 hertz, right? Yeah. So where this thing corresponds to the D5, which is also equal to a fundamental frequency, which is 587 hertz. So we know, again, D, or we know L, which is 60 centimeters. We know the fundamental frequency for that is 440 hertz. So we're going to know the distance here, where this thing is going to have a new fundamental frequency of 587 hertz. So we want to know this distance again here, which is the distance X. So where must I put my finger for this thing to play a 587 fundamental frequency? And then the last part of them says, without retuning, is it possible to play a G4th note, which has a fundamental frequency of 392 hertz on the same string? So basically the question is, where then would I put my finger? So let's say, I don't know, let's call it this point here. Let's actually use a different color. So where would I put my finger here? So let's call this distance, I don't know. What's your favorite letter? Miranda, what's your favorite letter?
C.
C, great. So we want to know this distance C, where this thing is going to play a new fundamental frequency, which was 392 hertz. So we want to know, basically it's asking that question, where would that C be? And it wants to know, is this possible for you to put your finger there? Right? I'll give you the answer to this. The answer is no. And the reason for that is that you're going to tell me. Okay. So what I suggest is just calculate the distance, and what you should find is that actually the distance is longer than the length of the neck. So you can't put your finger longer than the length of the neck. That's just not possible. That's the answer. Okay. So these are the 2 group assignments. Again, the first one, you're just dealing with traveling waves. Again, here I give you all the answers, so you can work for all of those. Second one, apparently I didn't give you the answer, but I am giving you the answer for part B. The answer for part B is actually no. But this one, yeah, it's not too bad. So let's go ahead and let me stop sharing my screen. So I'll stop sharing. I'll bring you guys up into breakout rooms again. Let you guys pretty much spend the rest of the time. So we got about, what, 35 minutes to work on the 2 of those. And I'll be around checking on everybody here. So how many do we have? We have 12, so we'll do 3 rooms, I guess. Yeah, 4. All right, and I'll be around to check on everybody as before. All right. Open arm.
Let's see the wave number.
Hello, everyone. How's it going? How are we doing?
I'm still pulling up.
Yeah, I'm just looking at the question again. There's a lot of parts to the first one, so I'm writing it all down.
There you go. And all the questions are up on Blackboard. All that good stuff as well. Just I know my son is passed out in our bed, so I want to go join him. That'd be great. Okay. Any questions, or are you just still kind of writing everything down so far? You said.
Yeah, right now just kind of still taking down everything, making a list of what I have and what I need.
There you go. Okay. Well, I'll be back to check on you then. Okay.
Okay.
Hello, ladies. How we doing so far?
Just starting.
Just starting. Okay. And all the questions are already up on Blackboard, so if you didn't scribble everything down when we were going through them, that's fine. All the questions are up on Blackboard, so you can find them up on there.
I'm pulling them up right now.
All right. Well, I'll be back to check on you then. Hello, ladies. How are we doing so far?
Okay, I guess.
Speechless. Okay. That's better than I have no idea what's going on. Okay. So how far have we gotten so far?
Decided on what question to answer.
Yeah, we're just on part A right now.
There you go. Of which one? The first one or the second one?
The first one.
Okay. And yeah, all the questions are up on Blackboard, so if you didn't scribble everything down, at least you can find them on there. So. All right.
Okay.
So I'll give you some hints on there. So for part A, let's see here. So you know the maximum transverse motion or the transverse speed of the air molecule, which just corresponds to harmonic oscillation. So basically what you know is Vmax. You're told that it is initially at 1 meter away from its equilibrium and it's not moving. So that means it has to be at its maximum displacement. So that means that 1 millimeter is the same thing as the amplitude. So you know the amplitude, you know the max velocity. The only thing you need to know from there is omega. And then omega, you know its relationship to the frequency. And that's all part A. All right. Okay, I'll be back.
Okay.
All right. Have fun.
Have the frequency.
How are we doing so far?
Still trying to decide where to start, I think.
Okay, which one are you looking at? The first one?
Yeah.
Okay, so let's think about what we're told. So let's look at part A. So we know the maximum transverse speed of the molecule, right? So it says the maximum speed of the air molecule is 100 meters per second. So that means it's the maximum speed. We're also told that initially it's at 1 millimeter and it's at its furthest distance away from equilibrium because it's not moving. So what is that 1 millimeter then? What would we call that?
That's the amplitude.
That's the amplitude. So we know Vmax, we also know the amplitude. So from harmonic oscillation, we know how that relates to the angular frequency, and we know how the angular frequency relates to the frequency.
Mm-hmm.
So good. So we can easily get the frequency from there.
Yeah. Okay. So I actually had written down the right formula. I just wasn't sure if the displacement was the amplitude.
Yes, in this
I was
case.
still getting there. I'm like, if it's not moving, is it?
Yes.
Okay.
Yes. If it was moving, then it wouldn't be the amplitude. Well, that's right. Okay. And then for part B, once you have that frequency, and then you know the speed of the wave, then you can also find the wavelength.
Okay.
Good, good, good. Okay. I'll be back.
Also, everything.
All right. Did we lose somebody?
Oh, we might have. She was having computer trouble.
Gotcha.
Yeah.
Internet issues and stuff. Gotcha. Okay. So, how are we doing so far, ladies?
We're trying to use the frequency equals the velocity times the number of nodes divided by the 2L for part A.
For which one? The one with the cello or for the other one?
The other one.
The other one.
Okay. Well, the other one is not a standing wave, so we can't use that one. So for that one, we're going to use the fact that we know it's a harmonic oscillator. So basically what we're told for that one is we know that the maximum speed of the single air molecule as it's harmonically oscillating back and forth is 100 meters per second. It also tells us that the particle has a displacement of 1 millimeter, and it is not moving. So that means in its harmonic oscillation, it is displaced by 1 millimeter, but it's not moving. So if it's not moving, does that mean it's at its maximum displacement, or is it somewhere between it 0 and its maximum displacement?
It's at its maximum displacement.
That is maximum displacement. So what do we call its maximum displacement?
The amplitude.
The amplitude, very good. So we know its amplitude, we know its maximum velocity and its harmonic oscillation. So that gives us a relationship with its angular frequency, right? Because we know that Vmax is equal to the angular frequency times the amplitude. And then we also know the relationship between the angular frequency and the frequency is just 2 pi, right? So we can write then Vmax is equal to 2 pi times the frequency times the amplitude. And then from there we can get the frequency. Is that okay? So that's part A. Now part B, we can now get from the fact that we know the speed of the wave is 340. The frequency we get from part A, so we know the speed of the wave then is equal to the wavelength times the frequency. So once we have that frequency, we already have the speed, so then we can solve for the wavelength. And then in part C, we already know the amplitude. Now, once we know the wavelength, we know the relationship between the wave number and the wavelength. So now we can get that. And then now that we have the frequency, we also know the relationship between the, the angular frequency and the frequency. So we know that. The last thing then is just to determine what is that phase factor, but we'll come back to that.
So what did you say about the amplitude again? I think I missed that.
Oh, the amplitude is when the particle is at its maximum displacement away from equilibrium. So here, since we're told that it has a displacement of 1 millimeter and it's not moving, that means it has to be at its maximum displacement. So in this case, that displacement we're given is the amplitude.
Thank
You're welcome.
Do we need to change the millimeters to something else?
You can leave it, well, that depends. Yeah, so when you are calculating the frequency, yeah, you would have to put it into meters.
Okay.
Yeah.
Okay.
Yeah. But then for part D, where it asks you to write out, you know, the displacement that way, you can leave it in millimeters. That's fine. Yeah. But yeah, when you're calculating the frequency, it would have to be in meters. That's correct. Yeah. All right. Okay, I'll be back.
No, it was okay in the end. It wasn't great.
Well, I was glad it went online because I probably wouldn't have gotten the grade I got.
Really?
Yeah.
There's a lot less work online, I guess. It was nice. You know.
Hello, everyone. How are we doing here?
Okay, we
Well,
figured out how to get A. We're good.
Yeah.
And now,
Yeah, we're doing B.
Good.
So we're doing what we did in lab, similar to lab, right?
Yeah, so now you're just saying you know the velocity of the wave, that's 340. You now know the frequency of the wave, so you can find the wavelength that way. Yeah. So V is equal to lambda times F. That's right.
Okay, so yeah.
Yep. Same thing as a lab. That's right.
so it would be wavelength equals V over F.
Yes.
So
Yeah, for velocity, like the general one is the wavelength times the frequency.
So it would have to be the velocity divided by the frequency equals wavelength. That doesn't give us the same thing, does it? I think you probably have to convert this kilohertz, I feel like, to hertz in order to get centimeters.
Yeah.
Yes. Yeah, so it has to be in hertz and not kilohertz. That's right.
We're on part B.
Yep. Yeah, so just make sure your frequency is in hertz. That'll give you an answer in meters, and then I just converted it to centimeters from there. So
Okay.
yeah, so in meters, it will be 0.0214. Yeah. Yeah. Yeah, and then part C is nice and easy. You already know the amplitude. You know the relationship between the wavelength and the wave number, so you already know that. That's just plugging in things in that expression. You know the relationship between the frequency and the angular frequency. So then the last part is just figuring out what phi is. So it's not too bad. Not too bad.
Just doing my math here.
There you go. Okay, I'll be back.
Okay.
All right. How we doing, ladies?
We're on part C of the first question.
Good. Okay. Yeah. Amplitude we know, and then the wave number is 2 pi divided by the wavelength. And then again, we know the angular frequency is 2 pi times the frequency. So the last part then is just figuring out what phi is. So. Actually, the phi I wrote down there is wrong. It would be right if I wrote down it was a cosine curve, not a sine curve. So, sorry about that. So since I wrote sine, then it should be, what, pi over 2, actually. So, should be pi over 2. Yeah, it means the last part's wrong too. So it should be a cosine curve, not a sine curve. Okay. Okay. Let me fix those and then I'll post those back up there. Okay. Stop letting my children. Okay.
How did you guys get the wave number?
I'm sorry?
The wave number on C.
Oh, the wave number. So the wave number is related to the wavelength by 2 pi divided by the wavelength. So that's the wave number. So as long as you know what that wavelength is, then you know what the wave number is as well. Or vice versa. Okay, it's all fixed. I put the new one up on there. So yeah, did everything in terms of cosine instead. So sorry about that. Okay. I'll be back. Let the other groups know.
How did you, or what did you say equals 2 pi times the frequency?
That's the angular frequency. That's the omega.
That's what I had. But I'm not getting the same answer
Again, the same answer?
for some reason.
Okay, so you should have, what, 15,900 times 2 pi. Right. So,
Oh, I was looking at my wavelength rather than my frequency.
oh,
That's
gotcha.
why.
Gotcha. That would do it. Yeah. Okay.
I used the wavelength equals 2 pi over the wave number, because that's what we were looking for.
Mhm.
And we just solved in part B for the wavelength. So we have the wavelength, and 2 pi is 2 pi, so then you can find the wave number that way.
Mhm.
But I think a lot of our problems right now are just conversions. We're like, how do we put it back in standard units for the thing?
Gotcha. Yeah, just make sure everything is back in fundamental units, so hertz and meters and all that good stuff. So yeah, should be fine.
Our wave number,
Mhm.
we got a number that's kind of different. Is it because of the rounding? Like we're close, but we're not like the exact answer.
Yeah, probably rounding, because even though I put 2.14, it was actually 2.138, blah, blah, blah. So yeah.
Okay.
So yeah, it's probably just
That's what we
rounding issues. And I noticed there was 2 typos actually on that one, so I re-uploaded it. So if you want to upload a new version of that question, when I wrote d of x of t was equal to a, that should have been cosine and not sine, because that's the way we wrote it down before. And then for part D, then it should have a cosine instead of a sine. But otherwise, so those were the only 2 things. But yeah. But, yeah. Good. Okay, just let you know about that. I'll be back.
0.
Just to let you know, there were 2 typos on that first one, so I
Okay.
uploaded a new one. Basically, the typos were whenever I had a sine, it should have been a cosine.
Okay.
Right. But other than that, those were the only typos that I noticed there. So, but yeah. So, how's everything going?
It's okay. Okay. Oh, we have a question.
Sure.
Are we going to have to do all these conversions on the test, or no? Because I know for Merlot's class, he just did everything in like.
In the fundamental ones?
Yes. Yeah, we didn't do like any conversions on these tests.
Really?
Yes. Yeah, he already gave it to us all in like kilometers and
All the
meters.
right units. Okay.
Yeah.
I haven't written a test, so I don't know yet.
Okay.
That's the way I can say it. I mean, maybe some simple ones, but yeah, I'm not sure yet. I won't know until I actually sit down and put it together.
Okay.
But if you strongly don't like conversion, then I see if I can work around that. So sure.
We don't.
Okay.
at all.
Yeah, we don't like conversions.
Yeah.
Yeah, because we're getting like answers, but they're like off by the conversion. So
Gotcha.
Yeah.
Okay.
So I remember we got like 2.94 instead of 290.
Okay. Yeah, because you're still working in centimeters and not meters.
yeah, meters. Yeah.
Gotcha. Okay. Well, that's fine. I mean, as long as you state the answer with the right units, then I mean, it's the same thing. So instead of saying, K is equal to 294.12 radians per meter, then yeah, you would have the 2.94 radians per centimeter. So it's still the same thing, but yeah.
Okay.
Yeah, as long as all your units check out, so it's fine. Speaking of exam, I forgot to mention in the beginning, I did post the old practice exam stuff, so those are up on there. But so you can take a look at those whenever you get a chance.
Okay.
Everything else going okay though?
We're just like kind of confused on the phase constant.
Oh, so again, what you know is it starts off at maximum displacement.
Mm-hmm.
Right? So what curve starts off at maximum displacement? Is it a cosine curve or a sine curve? A cosine curve, right? So as long as you have maximum displacement, it has to be a cosine curve. So since it has to be a cosine curve, you don't shift it in any direction, right? So I don't want to make it into a sine curve and it doesn't start off somewhere between. So in that case, it has to be phi is equal to 0 because it starts off as a cosine curve.
So anytime it starts with a cosine curve, phi is 0?
Yeah, as long as I say it's, a cosine of omega t, blah, 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 then it would have to be a cosine curve. That's right. If it was the way I had it written down originally, which was a sine of blah, 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 then you have to make a sine into a cosine, which means you shift it by 90 degrees.
Okay.
So yeah, just depends on the way that it's actually written. But yeah, but in this case, since it's at maximum displacement and it's not moving, that means it has to be a cosine curve. So since it has to be a cosine curve, then you know phi has to be 0 in this case. And that's it. And then the last part is now just putting all that into an expression. Not too bad.
Why is it minus?
So remember, minus means that it's moving to the right. Positive means it's moving to the left. Okay. I could go into a full explanation, but I don't know if you want the full explanation. But basically, right just means, yeah, anytime it's moving to the right, it has to be a negative sign. Anytime it's moving to the left, it has to be a positive sign.
I just don't know how we know that it's moving to the right. Like,
Oh, did I not say it was moving to the right? Thought I said somewhere it was moving to the right. Oh, maybe I didn't. Okay, let me fix that too. Longitudinal wave is moving to the right in here. There we go. Okay. Let me re-upload that one too. My deepest and humblest apologies. Okay. Let me re-upload that now. Sorry about that. In my brain, it said to the right, so. Okay, and a new version up on there. Okay. All right, sorry about that, Adrian. You're absolutely right. Otherwise, you would have zero idea that it's actually moving to the right. So, okay. Yeah. Okay. Good. All right, let me tell everybody else and I'll be back.
I think if I remember.
Okay, so there was a piece of information that I forgot to put on there
that it has to do
with the direction that it was moving. Yeah.
okay.
So it now says that it's moving to the right. Right. So, yeah. In my brain, when I wrote the question this morning, it was to the right, but I just didn't actually write down it was to the right. So, yeah. Sorry about that.
So we're wondering about phase factor.
Oh, so in this case, since you know it's at maximum displacement in the positive direction, then you know it has to be a cosine curve, right? So because cosine starts off at maximum, then goes down, and then comes back up, right?
Mm-hmm.
So in this case, since you know it has to be a cosine curve, then you don't want to shift the cosine in any direction to make it not a cosine curve.
Okay, so most of the time it's going to be 0 then.
Yeah, so it's either going to be 0 or, for example, you know, if I told you it was at the origin moving positively away, then you would know it has to be a sine curve. So you just have to shift the cosine curve into a sine curve. And you would do that just by shifting by 90 degrees. So.
Okay, so you would use that then to put it in like standard notation and keep it as the cosine of this whole thing.
Correct.
But move it so that it looks like a sine curve.
Correct. That's right. Okay. So that way, by the time you got the D, for example, again, if I said it started at the origin moving positively away, you know it has to be a sine curve. So you would just switch it to sine of omega t minus kx. That's right.
Okay.
That's right. And then the phase factor would just be 90 degrees because you just have to shift it by 90.
But how would you write that in the equation? Like you would say 90 degrees in the little. Like,
yeah, it would either be plus or minus 90 depending if you're shifting it one way or the other way. But yeah, yeah. But since everything else is in radians, then you would actually do plus pi over 2 because that's the same thing as 90 degrees, but that's in radians. Just has to be in the same units, but. that okay?
Yep. I think we're ready to start the second one.
Nice. Yeah, officially about 4 minutes left. So
I was gonna say, I don't think we're gonna finish it.
that's okay. You don't have to finish it now. All right, let me tell the last group that I made an oopsie, and then we'll be back. Okay. There was an oopsie on the first one again. In my brain, when I wrote the question this morning, I was supposed to say to the right, but I forgot to write it apparently when I wrote the question. So for the first one, take that the wave is moving to the right. So that's why it has a negative sign in my solution for part D. So I re-uploaded a new PowerPoint that actually says it's moving to the right now. So yeah. Otherwise, you wouldn't know if it was a positive sign or a negative sign because you don't know which direction it was moving. So sorry about that. In my head, it was moving that way. So all right. So how's everything else going?
We are on the next problem.
Good. Okay.
I think we figured out part A.
Good. So how'd you do part A?
We use the frequency equals the velocity times the node divided by the 2 times the length to solve for the velocity with the first frequency.
Good.
And then we flipped it basically and used that velocity to solve for the length with the second.
Exactly. Very good. Very, very good. That's right. The velocity has to be the same. Exactly. So since we're assuming the tension is still the same, even though I'm moving my finger, then that means the velocity has to be the same. So exactly. So whether it's vibrating with the one frequency or the other one, the velocity has to be the same. Exactly. So that's the key insight you need into that portion of the problem. Exactly. So now when you're going to do part B, you would do the same thing. The velocity has to be the same. So now, again, you know the new frequency. So now just find the new length that you'd have to put your finger. And what you should find is that that is longer than the neck of the string. So the neck of the string is what, 60 centimeters. So if I remember right, you should get something around 70, 72 centimeters, something like that. Which means that you can't play that frequency because you can't stretch the length of the neck. So that's it. Yep. So you would have to actually retune, meaning you'd have to change the tension in the string to change the velocity. Very good. Very
You said
good.
72.
If I remember correctly, but I'm not sure.
Okay.
So.
I think I got 67, but
Oh, okay, that might be true. I don't
Okay.
remember. So. But it's something greater than 60.
okay.
That much I remember. So yeah, very good. You guys are all done.
Thank you.
You're welcome. So tomorrow we'll start sound waves. So we'll start talking about sound waves and then get into all that good stuff. So, did I mention that the practice exam is up? No, I didn't tell you guys. Okay, so the old practice exam questions are up on Blackboard. So yeah, sometime between now and next Monday when the exam is, you'll definitely take a look at those and kind of go through those for some old practice exam questions.
Okay.
All right. Otherwise, I may or may not see you for lab. So have a good day. Bye.
Okay, so this is what I did. Let me pull it up. So this is what I did.
Up to the. Wait, why'd you do 1.2 instead of 120?
That's just, I'm just converting it to meters instead of saying meters. Yeah. Yeah.
All that out.
Velocity is 528 meters per second. Now this is where I was confused.
Let me do that so you don't see me. Okay. So you know the it's all in here now. I can't see. Okay. So yeah, this is what I did.
So Molly's correct. So the velocity of the wave on the string has to be the same. So why is that true, Molly?
Because aren't they on like the same instrument?
Yeah, it's on the same instrument. You're assuming that when you put your finger down, you're not changing the tension of the string. So as long as you don't change the tension of the string, then, and you're not changing the linear mass density of the string, so as long as the string is the same, then the velocity has to be the same. Exactly. So that's exactly the key insight that you need in this problem, that the velocity has to be the same on the string. And yeah, and then you can use that velocity to solve back for what the frequency is, or in this case, the length. That's right. Exactly. Good job, Molly. All right. And then for part B, you're going to basically do exactly that same thing again. So you're going to use that the velocity again is the same. Use the new frequency to find the length that you would have to have the string, you know, where you'd have to put your finger. What you'll find is that where you have to put your finger is greater than 60 centimeters, but you can't put it greater than 60 centimeters because the length of the neck is 60 centimeters. So that's what does not allow you to be able to play that frequency, because it would be off the neck. So that's right. All right, good job, ladies. You're officially out of time, so otherwise, feel free to stay, but otherwise, have a good day, and I might see some of you during lab, and otherwise I'll see you tomorrow.
Okay.
Bye. Where am I? Oh, everybody gone. All right. How we doing, ladies?
We're kind of stuck.
Okay. For which one?
Just part A. We went and found the wavelength. We have that.
Okay. Well, let me ask you a question. So what has to be true about the velocity of the wave on the string if I play it at the full length of the neck versus if I put my finger here and then play it at a shorter distance?
Aren't they the same?
They're the same. Exactly. They're the same because even though I'm taking my finger and moving it from here to here, I'm not changing the tension in the string, and I'm not changing the linear mass density of the string. Therefore, the velocity on that string has to be the same. Remember, the velocity is just the square root of the tension divided by the linear mass density. So as long as I don't change the linear mass density and I don't change the length or the tension of the string, then those two velocities have to be the same. So basically, what you're going to do then is what? Use that the fundamental frequency then is equal to the velocity divided by twice the length of the string to find the velocity. That velocity then has to be exactly the same velocity in both cases, and then you're going to use that the frequency then is equal to the velocity, which is now that number that you found, divided by twice of x for the second part, right?
Why
Now
is it
just solve for what
twice?
x is. Why is it twice? It's twice because the fundamental has half of a wavelength, meaning that the wavelength for the fundamental then would be twice the length of the string. So that's why it's 2 times.
Okay. Do you know what the answers should be around?
I can solve it.
Just to make sure.
If I remember correctly, it should be somewhere around 44, maybe, something like that.
I
But,
got 44.9.
okay.
I
Yeah,
don't know
let
if
me
that's right there.
double check here. That's where this kid's screaming. Okay. Let's see here. So, yep, that was definitely my daughter screaming. Let me do it this way. So velocity then is equal to twice the length of the frequency. Okay, so solve. So it was what, 587 was the second frequency, right?
Mm-hmm.
Yes.
Okay. And the 2's are going to cancel. So then I get, and the first one was 440?
Yes.
Okay.
Yes.
20 times. So that's 60. Yeah, so I got 44.9744 centimeters.
Yeah. Okay.
Yeah. And then part B, you're going to do exactly the same thing. So you're going to use that same velocity that you already solved for. And in this case, use now the new frequency, which was the 392. Is that right?
When you say the same velocity that
Yep.
we used the one that we solved for in like the first part, right?
Yes,
The
correct.
528. Okay.
That's right. That's right. Yep. So what you should find in this case then is that the length should be greater than 60 centimeters. And that's why you can't play it. So what was it, 392?
Mm-hmm.
Do you still multiply the 392 by 2x?
Correct. Yes. Yep. Oops. Yeah, so this time you should get 67.35, basically. So in this case, since the length of the neck is only 60 centimeters, you can't go out to 67.35 centimeters. It's, you can't stretch the length of the neck. So in that case, you can't play then that particular frequency. Not without changing the tension, which would change the velocity. So. All right. All right, good job, ladies. So that's it for today. And otherwise, I will see some of you in lab, and then I'll see everybody else tomorrow. So tomorrow we will start the next chapter. So we're going to start sound waves. And I don't know if I mentioned this to you guys or not, but the old practice exam is now up on Blackboard as well. So you can take a look at that sometime between now and next week when we have our first exam 1 week from today.
Thank you.
You're welcome. All right. I'll see everybody in a little bit.